Hi, my name is Joseph Maloney, and this is my presentation on Physics 2211 Lab 3 Black Hole. So for this lab, there are two parts. Part 1 utilizes the orbit of the star around a black hole to estimate the mass of the black hole. Part 2 is use the estimated mass of the black hole to determine the initial velocity components of the star and have a spaceship orbit the star and black hole in a figure-8 motion. The physics concepts we'll be using today is the velocity update formula, which is the final velocity is equal to the initial velocity plus the net force divided by mass times change in time. The position update formula, which is the position final is equal to position initial plus the velocity average times delta t. The net force equation, which is net force is equal to change in momentum over change in time. The net force parallel direction, which will contribute to changing the velocity of the system, which is equal to the unit vector times the derivative of the momentum vector. And then the net force perpendicular direction, which will contribute to the changing of directions of the object, which is equal to the momentum vector times derivative of the momentum unit vector. And then we'll also be using the gravitational equation, which is negative g constant times mass 1 times mass 2 divided by the radius squared times the unit vector for r. So for part 1, for the mass of the black hole initial, we have the initial condition, which is the g constant, which is 6.7 times 10 to the negative 11. The stars match, which is 2 times 10 to the 30. Delta t, which is 24 times 60 times 60. And then we'll see that the time, first observation would take a time equals 0. And then at the bottom here, we have how we're going to calculate the star's velocity. So for the mass of the black hole's calculation loop, we first are going to use the final and initial velocities. We also are including the net force, the derivative of net force, the parallel component, the perpendicular component, and then we'll use this equation to calculate the mass of the black hole. So for the loop, this is what we get. So after running that simulation, we get that the net force is equal to 9.03 times 10 to the 28. The force perpendicular, which is 4.27 times 10 to the 27. The force parallel, which is 9.02 times 10 to the 28. Coming to finding that our mass of the black hole is 1.48 times 10 to the 34. Then we're going to go on to part 2, which is the don't crash part. So again, we use our initial constants, which is the g constant, the mass of the planet, which is 8 times 10 to the 27, the mass of a moon, which is 6 times 10 to the 25, the mass of a ship, which is 7 times 10 to the 12, delta t, which is 60, and then a starting position, which is 0. And then we also have the initial conditions of the moon right here. And then we're also going to use trial and error to solve for the initial conditions of the spaceship in the ship speed x and ship speed y. So then also for our calculation loop, we're going to use the net force on a planet, the net force on a moon by a spaceship, net force on moon, net force on spaceship by moon, net force on spaceship by moon, net force on spaceship, and then the velocity and position update formulas. So once we do that, we come to this picture, which is after our calculation loop, we come to find this rotation. It's not a perfect figure 8 due to just not having the exact velocities, but if we had the exact velocity, we would see a perfect figure 8 rotating around the moon and the planet. So what does it mean? How does the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components? So for parallel, it directly affects the speed. So when an object has parallel component, it directly affects the speed. For its perpendicular, it's changing the direction of the object. And then for change of momentum, it does the same thing for both of these, but it's in terms of momentum and not force. So what if? What if this imaginary system has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? So if we were to do this, in the computational model, we would also have to include the black hole and star gravity because they are still the dominant forces. But we would also include the planet and moon forces, even though they're weaker than the black hole and star gravity, they are still significant to the system. Thank you.